Hi, I'm QimengYu from Northwestern University. I'll briefly talk about a recent work of me and my advisor, Dr. Kuchikiawa's, on minimizing bisubmodular functions via a polyhedral approach. Bisubmodularity is a generalization of submodularity. To get some intuition, it's worth revisiting submodularity first. Formally, a submodular function is a function that satisfies the given property. Intuitively, submodularity means diminishing marginal gain. To visualize this, consider a submodular function f that evaluates the total colored area. F of x and f of y are colored in blue in this figure. The marginal gain of adding item I to x or y is the area in orange. The marginal contribution of I is lower for fy than that for f of x, because x is a subset of y. This concept can be generalized to functions with two set arguments, which is bisubmodularity. For a bisubmodular function, the domain is the collection of pairs of disjoint subsets of n, which we denote by 3 to the n. Note that this bisubmodular definition looks very similar to the submodular definition. There's a slight difference in the union term, which makes sure that the two set arguments are disjoint. In this work, we are interested in minimizing any bisubmodular function f. Problem 1 is the generic form of any unconstrained bisubmodular minimization problem. This problem is equivalent with problem 2, which is minimizing the epigraph variable z over q sub f, which is the convex hull of the epigraph of f. Before delving into the more technical stuff, I want to explain why bisubmodular minimization matters. Bisubmodular functions were first considered by some researchers back in the 80s. Recently, these functions have attracted more research interest because of their wide range of applications, such as coupled sensor placement, coupled feature selection, and bicooperative games. The figure is a visualization of the coupled sensor placement problem. Before our work, other researchers have considered bisubmodular minimization as well, but with different approaches from ours. She extended the Lovász extension result to bisubmodular functions, which implies that the ellipsoid method can solve bisubmodular minimization. Fujishige Iwata and McCormick Fujishige, they respectively proposed a weakly and a strongly polynomial algorithm for unconstrained bisubmodular minimization. Different from all these prior works, we are the first to apply a polyhedral approach. We give the complete linear description of the convex hull of the epigraph of any bisubmodular function. Based on that, we also propose a versatile cutting point algorithm, which handles not just the unconstrained bisubmodular minimization problem, like these earlier algorithms. Throughout this work, we assume that f of a pair of empty sets is 0. This is without loss of generality. We can simply subtract f of empty sets from everything. We also use -1, 0, 1 vectors as the characteristic vectors for every biset, S1, S2. We assign 1 to I if I belongs to S1, -1 if I belongs to S2, and 0 otherwise. This is a one-on-one unique correspondence between the space of ternary vectors and the pair of disjoint subsets of n. Now recall that Q sub f is the convex hull of the epigraph of f. To capture this convex hull, we propose a class of inequalities called Polybymetroid inequalities. They rely on a structure called bisubmodular polyhedra. We can see from this definition that this structure is analogous to the Polymetroids for submodular functions. A Polybymetroid inequality has the form z greater than or equal to pi transpose x, where pi is an element of the bisubmodular polyhedron of f, If pi, furthermore, is an extreme point of the bisubmodular polyhedron, then we call such inequality an extremal Polybymetroid inequality. In our paper, we first proved that the inequalities we proposed are valid for Q sub f. In fact, we also show that the extremal Polybymetroid inequalities, along with trivial bound inequalities, that is, each x entry is bounded by 1 and minus 1, they together fully describe the convex hull Q sub f. And here is a quick sketch of our proof. We first show that the inequalities of the given type are facet defining for Q sub f if and only if they're extremal Polybymetroid inequalities. Then we show that the non-trivial facets of Q sub f must look like pi transpose x less than or equal to z plus a constant pi 0. And this constant pi 0 has to be non-negative. Lastly, we show that pi 0 in fact has to be 0 to complete the proof. Now we have fully described the convex hull. We can use the extremal Polybymetroid inequalities to develop a cutting plane algorithm for general bisubmodular minimization problems. They don't have to be unconstrained anymore. Such problems can be written as problem 3, where C is a set of inequalities given piecewise linear approximation of the function value, and X is a set of constraints on the characteristic vector X. It can include any constraints, including cardinality or knapsack constraints. For a cutting plane algorithm to work well, we also need to efficiently solve the separation problem, which is, given a fractional solution x bar z bar, how to determine the most violated extremal Polybymetroid inequality. Boucher has proposed a fast greedy algorithm to solve this problem. Now we can introduce our delayed constraint generation algorithm. While the optimality gap is above tolerance, we solve the relaxed master problem to get solutions x bar z bar. If z bar underestimates the function value, then we solve the separation problem and add the most violated extremal Polybymetroid inequality to C. We then update the lower and upper bounds for the objective and the incumbent solution accordingly. Then we keep looping. To test the performance of our algorithm, we experimented with the problem that we call bicoverage problem. Suppose we are given a graph G and parameters B1, B2, alpha, and beta. The goal is to find a pair of disjoint subsets of N, S1 and S2, such that their cardinalities are bounded by B1 and B2, and a bicoverage function is minimized. We use this figure to explain what this bicoverage function is. Let alpha be 1 and beta be 3. Pick any node I. If I is chosen for S1, then it covers all the nodes reachable by at most one edge from I. If I is chosen for S2, then it covers all the nodes reachable by at most 3 edges from I. Suppose we pick S1 to be the squares and S2 to be the triangle. Then the nodes colored in green are covered by the nodes in S1. The nodes in orange are covered by S2. The bicoverage function captures the number of all the colored or covered nodes, which is 10 in this example. This bicoverage function is bisubmodular, and this problem can be formulated as a MIP with many more variables and constraints than the delayed constraint generation formulation. For our experiments, we generated random graphs with n nodes and edge density p. Our DCG algorithm beats directly solving the MIP as shown in this table. For example, our DCG algorithm solves the instances with 70 nodes and edge density 0.05 within 5 minutes, while the MIP has over 60% end gap after running for 1 hour. For the instances that MIP can solve within the time limit, DCG is also significantly faster. So in summary, Our DCG algorithm works very well for general bisubmodular minimization problems. And that's all I have. Thank you.